Hello everyone, myself is Gudapati. The project we are going to discuss about is real-time network traffic volume prediction using time series and recurrent neural network. These are my teammates Suriteja Merugu, Pujita Mandadi and Rohita Pathuri. Coming to the introduction of the project, this research delves in the domain of deep learning and networking. The exponential growth of internet traffic presents a significant challenge for resource management in today's networks. Traditional forecasting methods struggle with the nonlinear nature of the network traffic, leading to the inaccurate predictions and hindering efficient resource allocation. This research proposes a novel approach utilizing deep learning techniques to predict network traffic. Our proposed models will be rigorously evaluated using real-world data, demonstrating their effectiveness compared to the commonly used support vector regression baseline. The results are expected to showcase how deep learning can significantly improve network traffic prediction accuracy, aiding internet service providers in a better managing resources and maintaining network performance. The problem statement of our project is selecting the appropriate dataset and reprocessing it effectively are critical steps in developing accurate prediction models, especially in the domain of machine learning. This study focuses on predicting network traffic patterns using deep learning techniques. It addresses the challenges of dataset selection, preprocessing, normalization, and the transformation to construct robust predictive models for network traffic. The literature survey starts with the limitations of traditional forecasting methods in handling nonlinear patterns in network traffic data. This research process proposes leveraging advanced deep learning techniques. Specifically, the study focuses on long short-term memory (LSTM) networks, known for their ability to capture complex temporal dependencies. By harnessing the power of LSTM networks, the research aims to develop a robust model tailored for accurate network traffic prediction. The advantages of this literature survey are adopting deep learning techniques such as LSTM networks. The research seeks to surpass limitations of traditional methods like ARIMA and capturing the nonlinear patterns. The proposed solution also aims to provide more accurate predictions by leveraging advanced capabilities of LSTM networks in understanding complex temporal dynamics inherent in network traffic data. Coming to the next literature survey, this proposed solution revolves around the construction of a neural network model tailored specifically for predicting traffic flow on an hourly basis. By utilizing the data from a Moroccan Center of Research, the researchers train the neural network to forecast future traffic flow patterns. The neural network model is designed to capture the intricate relationships and dynamics within the traffic data, enabling it to provide accurate predictions for various traffic conditions. The advantages from this literature survey we obtained are utilizing the real-world data from Moroccan Center of Research. The proposed solution ensures the relevance and applicability of the predictive model to real-world traffic scenarios. And also, Navali traffic flow prediction allows for granular insights into traffic patterns, enabling more precise and traffic management strategies. The third literature survey is a solution involves development of research series of tests to assess the influence of the stochastic component of neural network prediction accuracy. Throughout the experimental testing, the researchers aimed to demonstrate the neural networks can effectively handle noise variance and provide accurate predictions from time series data. By comparing the performance of neural networks to classic regression techniques, the study seeks to establish the neural networks as the viable alternative for traffic prediction tasks. The advantages from this literature survey we obtained are by systematically testing the impact of noise variance on neural network prediction accuracy. The study provides valuable insights into the behavior of neural networks and the time series prediction tasks. Secondly, the findings suggest neural networks can perform well even in presence of stochastic components, including their robustness and suitability for real-world applications like traffic prediction. Lastly, by highlighting the advantages, the neural networks are over traditional regression techniques. Study contributes in advancing the field of time series prediction and reinforces the viability of neural network in practical scenarios. The next will be continued by Pujita.
Coming to the research objectives, the main goal of this project is to use deep learning techniques to create prediction models for network traffic. Among the specific goals are choosing an appropriate dataset and recording the communication between the German research network and the campus network, and preparing the chosen dataset for analysis by pre-processing it to execute non-IP traffic and anonymous IP addresses, and then transform it into a time series format. Normalizing the dataset's characteristics will ensure consistent training results at various sizes. In order to precisely anticipate future network traffic patterns, the data must be transformed from time series prediction, taking it into account both one-step and multi-step prediction algorithms. And then coming to the next slide, methodology. The methodology involves several steps. Dataset selection, utilizing the real-world traffic data, focusing on traffic between the campus network and the German research network. And then data pre-processing, cleaning the dataset by eliminating non-IP traffic and anonymizing IP addresses and converting it into a time series format. The data normalization, standardizing the features of the dataset using Gaussian transformation to ensure consistent traffic performance. Data transformation, here transforming the dataset into a format suitable for time series prediction and considering both one-step and multi-step prediction techniques to forecast future network traffic patterns accordingly. And model development, implementing deep learning models possibly by including recurrent neural networks like long short-term memory and gated recurrent unit models to predict the network traffic patterns based on the pre-processed and transformed data. By following these steps, the research aims to develop accurate predictive models for network traffic and facilitating better network management and resource allocation. And coming to the next slide, data set selection. Here the example data from the data set, where the data set has been gathered from the real world traffic data and focusing on traffic between the campus network and the German research network. And the next slide, data set pre-processing. The collected raw data set consists of network packets in PCAP format. The network traffic captured 3429 billion packets over 4 days and 18 hours. In fact, the storage of this traffic was about 1615 GB. Hence, in this phase, we processed the data in order to transform it into a time series that represents the length of the packets at each minute, and this part of the process was done using the bash scripts in order to optimize the execution time. Indeed, these data was sufficient to implement our network traffic prediction. Based on, we noticed that it's about a periodic curve where the long-term regularities are evident. Here the graph represents time series consisting of 6839 values. And coming to the next slide, dataset normalization. Training of ML algorithms often perform better with standardized input data. In fact, normalizing features is not only essential for comparing features with different scales, it is also a common prerequisite for many machine learning algorithms. For instance, in this absence of normalizing the features for optimization algorithms, some weights may update faster, and then others will be the features values plays a very crucial role in updating the weights. Hence, we apply the Gaussian transformation for the process of data normalization in this phase. And coming to the next slide, dataset transformation. Time series prediction requires a set of past observations in order to estimate future values of the features of interest. Actually, there are mainly two categories are explained, one-step prediction and multi-step prediction. Coming to the one-step prediction, the most straightforward strategy is one-step prediction, which is about taking a vector that include the last observations as input to the model responsible for the yielding the prediction, and then multi-step prediction is about predicting upper than one step ahead based on the same historical samples. Next slides will be continued by my teammate.
Implementation. Modeling phase. At first, the dataset was divided into two parts, as indicated below, using test set validation techniques, which is the most basic strategy for estimating the reliability and the robustness of the predictive models. Indeed, we split the data into two separate portions. training set and test set. Training set. It contains 80% of the original data. Hence, this portion will be used for training the predictive models. Test set. It contains 20% of original data. Hence, the fitted models will be validated on the test set. Building the two models. The proposed architecture of the two RNN variants has the same number of layers as depicted below: encoder and decoder. Encoder. The encoder consists of a single layer containing 16 LSTM GRU neurons. Indeed, it is responsible for encoding the time series to the state of the network. Decoder. The decoder consists of 4 consecutive layers, where each layer contained by default 8 LSTM GRU neurons. This will decode the encoding vector in order to generate the output sequence. Training the predictive models. Above picture shows the training of the predictive models of LSTM and running the train set values using model.pred of trainx and storing the output values in pred_train variable. And the above picture shows the training of the predictive model of GRU and running the train set values using model.pred of trainx and storing the output values in pred_train variable. Evaluation of the models. For evaluation purpose, the mean absolute percentage error (MAPE) is used as the evaluation indicator of the proposed models. Indeed, we have found accurate results for our primary test. Fine-tuning process. Throughout the section, we will try to refine the hyperparameters of the forecasting models in order to improve the accuracy. Indeed, we conducted our optimization using grid search approach. This later performs every convincible combination of hyperparameters. As a result, it is a massive computation in order to complete the task. Hence, we define a grid of n dimensions, where each dimension represents a hyperparameter. In our case, n is equal to step back, step ahead, number of neurons in the encoder layer, number of neurons in the decoder layer. The table below demonstrates the range of possible values that the hyperparameter could receive. The next slides will be continued by Rohita.
Coming to the conclusion part, in this study investigates the use of deep learning methods such as recurrent neural networks like long short-term memory and gated recurrent unit models for to anticipate network traffic. And the empirical examination also revealed that the GRU model outperforms the LSTM and with greater performance and a reduced mean absolute percentage error of 3.18, and the established approach also guarantees quick calculation, making it appropriate for real-time prediction applications. And furthermore, the study reveals that GIO models outperform classic machine learning techniques such as support vector regression (SVR). Overall, the findings demonstrate the success of GRE models with efficient data preprocessing and feeding strategies for network traffic prediction, which provide high accuracy and computational efficiency, making them useful for network management and resource allocation tasks. Coming to the next slide, future work. In this, the work sets the path for further research in this subject, and the future study might explore like hybrid models, attention mechanisms, and traffic anomaly detection. Coming to the hybrid models, in this combine GRU with other deep learning architectures such as convolution neural networks, and it can capitalize on both temporal and spatial relationships in network traffic data. And attention mechanisms, in this adding attention mechanisms to the other GRU model and to focus on particular features of the input data that are most important for prediction. Coming to the traffic anomaly detection, in this use, we are using the trained model to detect substantial deviations from anticipated traffic patterns, which may indicate network abnormalities or security concerns. By studying these options, we can improve accuracy too. Thank you.